All right, so I'll get started. So one of the things I've been working on for the longest time is a textbook. I've mentioned to you before that I hate the textbook industry, mainly because of just how expensive it is. And so it's my goal to eventually finish writing this data structures textbook for 2168, which I've been working on for a number of years right now. And and it's definitely my textbook because I'm rather eccentric about it. When I find out that something exists, I really do need to track it down. For instance, with the factorial function, which is something we know from math, which is n factorial is equal to 1 times 2 times 3 times 4 all the way up to n, right? I want to figure out where, how early were we finding out about? Very early in Hebrew texts, by the way, as well as a ton of other places. And similarly, when we find things like the Fibonacci sequence, which is a very famous sequence in mathematics, it is the sequence where each number is the sum of the two preceding numbers, so 0, 1, 1, then 2 because 2 is 1 plus 1, 3 because 3 is 1 plus 2, 5 because 5 is 2 plus 3, 8 is 3 plus 5. A lot of these sequences are discovered most of them are named after Europeans. That's the way it is. And partially because that's when people would refer to it, they would look at European texts. But like I said, I'm a bit of a guy who likes to look up stuff. And a lot of this stuff, as it turns out, as over the years, we find that Indian mathematicians, because they were working with the base 10 system a lot earlier, discovered these sequences a lot earlier too. So you're going to find that a lot in algorithms, especially you'll find things like here, if I look it up, I don't need to look it up, like the Hamiltonian path problem in algorithms. That was also an Indian mathematician, Rudrata, who found that, so sometimes it's referred to as a Rudrata's path. So those things happen. Basically, things will have multiple names throughout history. And not only that, it's completely possible that when things get discovered, because data preservation isn't what it is now, things just got lost and forgotten. They burnt, or they rotted away, or were forgotten, So it's quite possible that these things have been discovered. But we're going to, so these mathematical sequences have history, and I love looking into that because, it's just fascinating to see how many, that people just are brilliant. They come up with all these brilliant ideas over time and stuff like that. What we're going to be talking about today is the number pi, and this is going to be more of a classical lecture today, where but I'm going to build a project, and I'm going to show you how I'm building it. But the objective is to teach you about for loops, and the way we're going to do that is by learning about pi and different equations in mathematics. It is going to get mathematically technical at some points, but I assure you it's not above your capabilities. A lot of mathematics, because they use Greek symbols and stuff, looks complicated. But this one is just simply, we are going to code something that follows a pattern. And as long as you can follow that pattern, which is very straightforward, you can do that. So let's talk about pi. Right? Pi is, so let's look at the number at pi. So pi, again, I love Wikipedia for mathematics, is, as you've learned, a mathematical constant. What it's doing is that it is the ratio between the diameter and the radius and the circumference. Well, diameter and circumference. Yeah. So the idea here is if we have a circle of diameter 1 and unroll it, okay? Then you're going to so you can see from this animation, if we take the circle of unit 1 and unroll it, the amount you unroll is going to be equal to pi, right? That's kind of what we mean. Given this property for a circle, this size for a circle, this ratio is going to be constant, essentially, for all circles. So if it's something of size 2, we're going to multiply this amount by 2. Pi has some very interesting qualities. It is what we call an irrational number, meaning that you cannot represent it cleanly as two different fractions, right? We can try to, but you can't give it a nice clean answer for it. It It's consequently, its decimal representation never ends, nor enters a permanently repeating pattern, right? So it's very interesting like that. And so one of the things that is used to, that people do with like powerful computer clusters to test how powerful it is to compute how far you can get with the digits, or to use what's called an approximation algorithm to figure out pi. Because figuring out the value of pi isn't exactly easy, right? You can get that it's 3.14, not too bad, or it's a little bit more than 3, fairly easily. You can discover, any culture can basically discover that pretty early on, but it takes it has to build on other mathematical knowledge to get higher and higher and higher, right? In fact, we can look at this. There's a history of pi. Chronology? Yeah. Chronology of the computation of pi. And as we see, as our tools improved over time, this is a log scale. This is the number of digits we've been able to compute for pi has gone up drastically. Like, ever since computers skyrocketed in the number of digits of pi we've been able to compute. Again, that's more, this over here isn't really giving us, I don't think, any useful knowledge. It's more of a flex. It's definitely just kind of trying to figure out how strong things are, as well as how good is your algorithm for discovering pi. Right, so where is it? Irrationality. Approximations, here we go. Approximations of pi. So, let's see, in Chinese mathematics, about 7 digits. So various times in history there's been fractions used to approximate pi. 22 divided by 7 was mentioned in the previous page. If you divide 22 by 7, I won't make you, it's 3.142857. So it's off by 0.04%, which actually isn't too bad on a lot of scales, right? Because remember, things don't have to be accurate, they have to be accurate enough. Remember, when you're building something, you're never going to build a perfect circle. It is just impossible with the level of discreteness you can get with the bricks, right? Like Babylonian mathematics usually approximated 3, sufficient for the architectural project of the time, also reflected in the description of Solomon's temple in the Hebrew Bible, right? So you've got an old Babylonian tablet gave the approximation as 25/8, right? Other approximations exist throughout history in different texts. Different religious texts have it. It's pretty cool. China had its own mathematicians that gave their own approximations. 355 divided by 113 is, let's see, where was that one? But that one is pretty darn accurate. But it wasn't until like Middle Ages and until the Middle Ages and Renaissance that we got the equation that I really want to take a look at today. It's called known as the Madhava-Leibniz sequence because when we became aware of it, it was because of Leibniz, who's a very famous mathematician. But it was independently discovered that it was independently discovered earlier. And it's this equation over here. This Leibniz formula is it's because it uses that Greek symbol, it can be a bit scary over here. So ignore this bit, right? This is not what I need. The idea here for the Leibniz sequence is pi over 4, in other words, a quarter of pi. In other words, like if you're just looking at if you draw a 90-degree angle, right, and that segment between it, right, just a quarter of it. Okay, and the reason we do it is because it's a bit easier to read this next bit. A quarter of a pi is equal to 1 minus a third plus a fifth minus a seventh plus a ninth, and if you keep going until you hit infinity, when we reach infinity, which you cannot do, right? But if you were to hit infinity, then the total value of everything we added together would be pi over 4, right? So this is an approximation algorithm, meaning that the more numbers we add, the closer we're going to get to pi over 4. and then we can get the value of pi by just multiplying that by 4. Does that make sense to everybody? So we have a pattern, right? The more we continue the pattern, the more accurate we're going to get. Does that? Everybody's following, right? Like I told you, this part looks complicated, but it's just a fancy way of doing this. It really is. Okay, so let's see, so the pattern, and we can see the pattern here. This is just a mathematical way of explaining this pattern, which is we alternate between subtracting and adding, right? We are alternating between subtracting and adding, and we are adding 2 to the denominator each time, right? So the denominator is 1, 3, 5, 7, 9, right? When you put it in that, right, and that's what we're describing over here. This alternates because negative 1 times 1 times negative 1 times 1, well, negative 1 times negative 1 times negative 1 times negative 1 alternates between 1 and negative 1, right? And then this is the way of just simply saying we add 2 to the denominator and we're starting at 1. Again, it'd be really nice if when you're beginning math, if they explain things like that, but the goal of doing math is to be able to take these random symbols that we've been figured out and that we get taught and, kind of do that. Mathematics is kind of its own language in that. There's various proofs, and if this was a math class, we'd go over these proofs. But this is not a math class. We're not doing these proofs. This is a programming class where we look at this math and we say, okay, I believe you, and then we're going to just kind of see if it works out, right? So the idea here is that we are going to program this sequence in using our for loop. So let's go ahead and review the for loop, okay? So I'm going to pull up idle, which I've already done, and I'm going to create a new file, okay? New file, and I'm going to call it, Control S. I'm just probably going to call it, let's go to Documents, GitHub, we're going to go to Classroom, Intro, Pi, Approx. Okay, and what we're going to do here is I'm going to start by showing you how the for loop works, right? What we were learning about the for loop is that it has 4 parts to it. For something in something is the way we write it. And we're still going to keep this 4th part as range. And that's the way it's going to be for a while. And the way we described it is that if we have this range 5, if we have this range of some number, it's going to do this some number of times. Print hello. And I'll explain why we use the word range eventually. It's not too far off. But the idea here is that whatever we put in range generates this, means that we have to do it that many times. So if I do hello in here, this will be hello 5 times, right? Okay, if I do 2, it's going to repeat what's ever in the for loop twice. If I did hello print world, we'll get hello world, hello world, hello world. A fun kind of thing we do with loops, I say fun, but I guess nifty is a better word for it, is we can use it to kind of go over values, right? I can take a value like I. We typically use I for integer in this, as opposed for I for the imaginary number, I for integer. If I set that equal to 0, and what I do here is I say, we're going to I'm going to take I and say I is equal to I plus 1. Okay, first off, we need to review this statement, right? What does this say? We take a look at the value. We look at the right-hand side first. We say, let's take a look at what's in I, which is 0 to start with. We're going to add 1 to it, and we're going to restore the result, whatever it is, in a variable. That variable just happens to be I, which is where we just got our variable from. And then our second line is going to be printing the value. Print I. 1, 2. In fact, maybe it might, we can flip it around and we would get 0, 1 because we would be printing out before, right? So I is equal to 0, print out its value, add 1 to it, print out this value, add 1 to it, and just do it twice. Do it 10 times. And this is kind of the way for loops work in a lot of languages. That being said, we can skip a step here. We can skip a pretty big step here by utilizing the second slot in our four-word phrase, for blank in range 10, which is this. I. For I in range 10. So let me go ahead and actually go ahead and explain what's going on here. A for loop iterates over a collection of things. That's what it does. That's technically what we are doing. We have a collection of things, and we're going to go through that collection of things one at a time. Okay? So here I'm saying I'd like to go over for everything in range 10. And I'm going to use I to represent the current thing I'm looking at in this collection. What is the collection? Range 10. What the heck does that mean? Range 10 is basically a sequence of numbers. I can actually, go over here, type range 10, and it's going to give me something less than useful, I guess, right now. Range 0 to 10. But if I go ahead and say, because I'm going to use some black magic here that you'll learn later, print list of range 10, we'll see that generates what we'll call a list, which is basically just a collection of stuff, and it gives me a range of numbers from 0 to 9. It is 10 numbers long. So it gives me 10 numbers starting at 0. We always count from starting at 0 when we are doing when we're doing computer science. The vast majority of languages start counting at 0 because it makes the math easy. It will make the math. What math does it make easy? I'll show you in about 5 minutes what math it makes easy. So what we do is that when we say for I in range 10, we create this range of of values, and then I starts at the first value. It will be 0, then it will be 1, then it will be 2, then it will be 3, then it will be 4, and so on and so forth until it gets to the end. Okay? So anything that is iterable, for loops can be used on. In other words, anything that's a collection of things that you can just kind of go through. For example, for letter in, let's go ahead and make it easier to see, word. I'm going to create a variable over here, word. What kind of things are words? They are strings, of course. Hello. Oh, well, you can do better than that. Why hello there? Okay, for letter in word. Print letter. And right now we're just working with print statements to see how this works. But you can iterate over anything that is a collection of things. We can iterate over a range because it is a collection of numbers in order. And here, in this example, right, we're going to get a lot of stuff printing out. We iterate over every letter in this word. For every letter, and letter is the variable name. You'll see in a second I can change it to whatever. W, it goes to the first letter, then the second, then the third, then prints out the space, because that's technically a quote-unquote letter. That is a glyph. It is a character, right? H-E-L-L-O, and then the character space, and then there. And then it goes to the next line and starts printing out all the numbers from 0 to up to, but not including 9. Sorry, not 0 through 9, up to, but not including 10. Okay? So, we're not going to be using this one today, and we're not going to be using that one for a while. Most of what we're going to be doing, especially on the first exam, focuses on range, right? And the various things we can play around with range. So, because right now there's really two things you can know that you can use the for in range for. You can go for blank in range to say, I want to repeat this a certain number of times, and then you can use for variable in range to basically say, I want a variable to change over time. And by happenstance, this loop will go 10 times because there's 10 numbers. So, and it doesn't have to be I could call it num, right? I could also call it not number, right? I call it not a number, and press and I could run it, and it'll still run as long as the names of the variables match, right? The variable name doesn't matter, right? Or I should say, or rather, the information doesn't get any. Sorry, the for loop doesn't get any information from the variable name. It's for you, and we typically use I when we're being kind of lazy there to just simply say, hey, this is our number. So this is pretty cool. Now it goes from 0 up to, but not including 10. So you can think of it as a range statement, right? You can think of range of something of a range of x saying, hey, we are going to go from all, and this is the algebraic notation for it, from 0 to 10, inclusive on the 0, exclusive on the 10. Does that notation seem familiar to people? Right? Yes, you've taken some amount of algebra, you've probably seen this notation. Okay? It means we're just not including 10 in there. Now, when I printed out range, though, when I printed out range 10, it said, I'm going to create the function range, it's going to go to range 0, 10, which implies that this can take two numbers, and it certainly can, right? 0, 10, right? Does the same thing. Make sense? So, of course, the next question you ask is, what happens if I change that first number now, right? That'll change the starting point. And if I change the second number to like 17 or something, that'll change the endpoint, right? So we can say range x, range, and let's go ahead and be a bit more we can use more, bigger variable names. We're going to call it start, stop. Goes from start to stop, excluding the stop. Now now the range from, so let's go ahead and look at from 5 to 10. Again, we get 5, 6, 7, 8, 9. It prints out 5 numbers total. Yes?
So when it comes to us using range in the for statement, it doesn't matter if we use the, how should I explain it? So when we do like the bracket and the parentheses the first time, it stops at like the 10 when you do it.
Right.
However, it includes 5.
So the difference between is that this one assumes you're starting at 0. This one assumes you're starting at another point, but they both stop at the second at this location. Okay. So here we're only defining the stopping point. If you have two numbers, it's going to say, oh, you're defining a starting and a stopping location.
Okay.
Okay. So for I in range 5 to 10 gives us 5, 6, 7, 8, 9. Now when I say this makes the math easy, if I were to ask you how many numbers does this produce or how many times does this for loop run, you'll be able to say 5 fairly easily because you can simply take the stopping point and subtract the starting point. 5 minus 10 is equal to 5. There's 5 numbers. Going back to 17, right? How many numbers is this? It's a bit too many to count all at once, but it is 12. And we can count that up by chunking it into 5. 5, 10, 12. Grand total of 12 numbers there. So that's what I mean by it makes the math easy when we start at 0. When we start at 0 and don't include that second number, that range. Okay, so it goes up to but does not include 17. So final question on, I suppose we should experiment just a bit more. Okay, let's experiment just a bit more. What if we do, is there a limit, right? Can I do -5 to 20? Can I do negative numbers? Of course you can. Nothing's stopping you from doing negative numbers, right? Can I do, what's stopping me from doing this? Your computer hating you is what's stopping you from doing it because it will take a while to print out all those things. Printing is actually a very expensive operation, and we will be here for quite a while if we want this program to end. We can just simply hit X to terminate it, though, and that's fine. But there's really no limit on how long these things can run, so long as it's a mathematically valid statement. As long it's not going to go on forever in this kind of format. So other point of experimentation is, what if I do, so we did 0 to 10, what about 10 to 0? What in the world does that do? And the answer is it does nothing, right? Because that's not a valid range, right? It's from the starting point to the stopping point, but we've already hit that stopping point, right? So does that mean we can't go backwards? Well, if there's a second variable, is there a third variable? Yes, there is, and that's where it stops. There is a third possible variable. And so you can, and they all have different contexts based on how much control you want. Most of the time you just need this. Sometimes you need this, and sometimes you need this other level of control. But it's very easy to kind of see with what it's going to do without me needing to explain it. If I say range 0, 10, 2, okay? 0, 2, 4, 6, 8. If I change it to 1, you'll get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I change it to 2, we get 0, 2, 4, 6, 8. If I change it to 3, we are going to get 0, 3, 6, 9. And if I change it to 4, we are going to get 0, 4, 8. This third variable is called the step. Basically, how much, by what step are we going to try to hit this other number, right? And it's useful if you just want to do every other number, as you can see, right? So I could say, if I wanted to go do all the odd numbers from 0 to 100, all the odd numbers, I'd start at 1, go up to, but not include 100, and say, go up by 2s. And you can see here that it does that just fine. It goes up by 2s. Okay. There's always a question on the exam of the format of something like this, where I say, hey, for I in range, begin, start, stop, step, and I ask what numbers get printed out. Okay. Obviously, I'm not going to ask you to go up to 100 or something, right? On the exam, I typically don't ask for more. Sometimes it's 2 numbers that get printed out, sometimes it's 3, sometimes it's 4, right? But it's not going to be ever 500 or something like that. I don't want you to burn your time. The time is supposed to be spent thinking, not writing repetitive numbers. That doesn't really test you. So this is a useful tool, and we will make use of it today. For that. But those are the 3 things we know. And while we're not going to use it today, it's also useful to know that, going back to our previous question, can I go backwards? -1. Start at 0, go up to, but don't include, starting at 100, go up to, but do not include 0, and count by your step of -1. Rather than going up by 1, we're going to go down by 1. So if we run this, we start at 100, because that's our starting point, 100, and scroll all the way down, and we go down to, but do not include 0, right? Why don't we include 0? Because you never include the stop point, right? Just consistency rule. And we can do 100 minus 0 and go, oh, there's 100 numbers there. We're not going to do counting down. I'm not going to try to pull a trick on the exam by having you count down. Just useful to know that you can do that. Okay. So going back to the whole calculation we're going to do today, right? We need to basically build up a program that will add continuous fractions together, and that seems a bit tricky. So I've come up with, I'm just going to give you the game plan, which is, no, I don't want settings. I want a whiteboard, please. Whiteboard. So our game plan is going to be fairly straightforward. Okay. So where I want to get is here. I want to be able to get to, I want to calculate pi over 4, and that's going to be 1 minus a third plus a fifth minus a seventh, dot, 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 right? I want to do this calculation. But trying to do this all at once is very complicated. It's a lot to do all at once, I should say. Okay, so instead, we're going to break it down into steps that we can turn into other steps. Our first step is we're going to ignore the fractions and the subtraction. We're just going to start by writing something that does this. 1 plus 2 plus 3 plus 4 plus 5, right? Make sense? Then we can turn that into 1 plus 3 plus 5 plus 7, right? We can figure out, can we skip numbers, right? We can either, so this is step 1. I'm going to call this step 2A because we could do that first, or we could do step 2B first, which is we figure out how to do this part, right? How to alternate the signs. So either figure out how to alternate the signs, and figure out how to alternate the signs versus figuring out how to count by every other number, which we've kind of already know how to do if you're paying attention. And then finally, we'll get to third step, which is we are going to stop adding whole numbers and we're going to instead add fractions, which is actually probably the easiest step, but visually the most cluttering, so we're going to leave it for last, right? Because we have to add in the bit where we see that we're adding fractions. And honestly, we could do that, could be 2C, we could do that before any of the others, but I like to do that one last. So when we're learning these things, it's a bit tricky to get from A to B, so we're going to just start, or A to C in this case, so we're going to go through step by step. So our first goal is, and what I'm doing here is I'm going to comment out this code. What does that mean? I'm just simply turning off this code by placing a comment in front of it, right? So comment, remember, is this symbol over here. It's your hashtag mark or your phone mark or the hashtag, right? So what this does is that it tells the computer, ignore everything that's behind me, right? So I could have some amount of code here, right? I could have a print function over here, and then I could have this as a comment to explain what it's going to be doing. Or I could have it above it and explain what it's going to be doing. But it's also a useful debugging tool because you can, quote unquote, turn the code off by putting a comment on it, and then remove the comment to turn it back on. It's useful for that kind of thing, but let's look at this. So the first thing we want to do is just generate these numbers before we start adding them. So 1, 2, 3, 4, 5, 6, 7 to some limit. Right? We want to hit some limit. It's equal to, let's say 7 right now. So we want to generate some amount of numbers up to, but not including the limit. So for I in range, and we're going to do, and I'm going to start off simple. I'm going to say, rather than putting in a solid number, I'm going to put in limit over here, because you can just throw a variable in, right? There's nothing here that says you have to put a whole number in here. You can instead, a literal number in here, as we call it. We can also put in a variable. What is a literal? A literal value, as opposed to a variable, right? A literal value would be something like 3.5, or 7, or 12, or hello, whereas a variable is, as you know from math, a variable. It's something that, it's a word, it's a placeholder that we use instead of a literal. So for I in range, we're going to print I. We're going to need to do something other than print with it later, but for right now we're getting 0 to 6, and really what we need is we need to be able to print out the numbers 1 to 7, not 0 to 6, right? Because there is, in our pattern, we go 1 plus a third, 1 minus a third plus a fifth minus a seventh, right? We alternate between plus and minuses, but we don't have a 0 and we start at 1. So let's go ahead and start at 1. And we get 1, 2, 3, 4, 5, 6. Our limit is 7, and I'd really like it if my limit was 7, I'd have 7 numbers and it would go from 1 to 7. So we're going to do that. The way we do that is we go range is limit, so range is 1, we start at 1, that doesn't change, but we're going to go to limit plus 1. Make sense to everybody? So that will give us the numbers 1 to 7. And it will run limit plus 1 minus 1 number of times. In other words, limit number of times. So we've got these values. So the next thing we're going to do is remember, what is the point of generating these values? The point is that we need to add them together and eventually move to adding and subtracting them together, right? So what we're going to do here is yes? Oh, sorry. What we need to do here is simply, we need to do a technique we're going to do pretty often in our code, which is called doing a running sum. So what I'm going to do is I'm going to create a variable called total, which will basically be our total sum. I don't use, in other languages I would use the word sum to say, hey, the sum of all the numbers is this. But if you look, when I typed it, it might be a bit hard for you to see because it's subtle on here. The sum pops up as purple letters. If something pops up in purple in Python, that means it's a reserved, it's a word that's already been used, like print or length or range, right? Those are words that Python has already said, those are my words. I guess you can use it, but then you won't be able to use my version. So I'd rather so instead I use total, which is a word that is close enough. And what we do is, with a running sum, is fairly straightforward. We say the idea here is we want to generate 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Let's go ahead and change this to 5 because that's a very easy value to compute. 1 plus 2 plus 3 plus 4 plus 5 is 2 plus 3 is also 5. 1 plus 4 is 5, and then we've got a 5. So 5, 5, 5, it's 15, right? Not too bad. It's not terrible to compute in our heads. So we've got these values. Let's go ahead and add them up. Total is equal to total plus I. And this is the way a running sum typically works. You take what you currently have in the total and add the amount you want to add to it, which in this case is I, and then store that amount, and store that new amount in total. And when we run it, we get absolutely nothing because I didn't put a print statement in. This is a very common mistake. You will see it. You will accidentally do it all the time. But generally, the answer for the first question you have to ask when you ask, why isn't my code doing anything, is, did you tell the computer to do anything, right? Now, if I put the total inside the print statement, we can see it step by step. It adds 1, then it adds 2, then it adds 3, then it adds 4, then it adds 5, right? It adds 1, 3, 6, 10, 15. Make sense to everybody? If we only wanted to print out the last step, we just simply move it outside of the loop. And why don't we do both for a bit? Why don't we go ahead and we can print out both, I think, but yeah, why not? We can say total, comma, I. Over here, actually, I'm going to do something a bit clever here. So I'm going to print out total. Sorry, I got to do a print statement to actually print stuff out. Print out the current value of total before we do the operation. What the value we're going to add, and then I'm going to print out what the value will be once we add them together. I'll add in some spaces to make it slightly more readable. And so 0 plus 1 is 1, and then so that's going to be 1 in the next step. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15. Make sense to everybody? We can actually expand this out a bit further and make it even more readable. Total, and then I use the plus sign over here, and then I use wouldn't you know it, the equal sign over here, and suddenly we're printing out equations, right? 0 plus, does everybody follow that so far? Right, I'm just simply printing out what it's going to be. Debugging things like this is very useful. Of course, it also is predicated on you actually like doing it correctly yourself, because there's nothing that stops me from putting in a minus there, and of course it does not make sense whatsoever if I put in a minus there, right? So what I'm saying is it prints out correctly because I used the correct terms, right? Okay, so we've got this value, we're going up, and we've got our running sum, and we're going to just simply print out the total at the end as well. Great. So let's talk about, so let's go ahead and back to the whiteboard and see what we have. So we have two options. We can either work on every other, we'll go ahead and do every other number, because that's not too bad to do. Okay, to do every other number, right, we have the third range ability, which is, right, what is range? We can do start, we can do stop, and then if we add in a third, it is the step. And it is going to be essentially by step, right? And what does that mean? So if I put in a 2, it's going to go up by 2s. And that's really all we need to do here. We just simply put in a 2. By the way, the white space I put in here doesn't matter other than making it easier to read. So that's why I have so much space in there. So now if I do this, it will be the numbers that get generated are the middle column. That's I. 0 plus 0, 3, and 5. So this is 1 plus 3 plus 5. And, right, 1 plus 3 is 4. 4 plus 5 is 9. So grand total of 9. And so what's great is that we know it works for this. So we could, going up to something like 50 is no issue for our program, right? It just does it. So computers are good at math, okay? Okay, our next thing we have to do is going to be a bit trickier, and that is getting this to alternate, okay? 1 minus 3 plus 5 minus 7. Now, if we were a bit more advanced, if we had gone a bit further in our programming, we might be able to use something called an if statement, which says, hey, if we're like this, do this, otherwise do this, right? We kind of make branching choices there, but we're not there yet. So what tools do we have? Really, we just have for loops and math, and the mathematical tools what we're going to use. We're going to use and for me, because I've done this so often, it's pretty much instantaneous as to how I need to do this. But a lot of you, you're not used to looking at numbers and like, oh, that is a tool I can use to modify this, as opposed to you look at numbers as problems to be solved, because that's what you've had to do. So the tool we have is -1, which flips the sign when you multiply it by something, right? You can think of this as 1 plus -1 times 3 plus 5 plus -1 times 7, right? Make sense? All the negatives are just, all these are just adding a number, or, okay? Or another way to put it is plus -3 plus 5 plus -7, right? So we just need to make every other number negative somehow. Rather than subtracting it, we're just going to make it negative, and we're still going to add the negative number to subtract it. Okay? So how do we make a number negative? We got to multiply it by -1. And we're going to use the fact that if we multiply a negative number by -1, that does turn it positive, because what we can do is that we can have a variable that determines the sign of it. I'm going to start it out over here, and I'm going to say the sign is equal to 1. And what we're going to do is that every time we go through this loop, because we're going to run a statement. In fact, it's probably easier to do if I start its own for loop out over here. Don't write this down because I'm going to delete it and put it into our own thing. But if I do something like this, sign is equal to 1, right? It's a bit easier to see if I do this first. For in range, it doesn't because I don't care about how many times I do it. But 10, if I do, I'm going to print the sign, and then I'm going to do sign is equal to sign, what we previously had, times -1. And we can see, still generate, so we can see that we started with 1, then we multiply it by -1. So we get -1. Then we take -1 and multiply it by -1, and we get 1. So we can see it's alternating between 1 and -1, right? So now what we're going to do is we're going to do the same thing over here. We have our sign, right? We have our sign. It's equal to 1. For I in range 1 to limit plus 1 by 2's, what we're going to do here is the value that we need to change is I, right? That's what we're generating. So we would like it to be 1 minus a third plus a fifth minus a seventh, or 1 plus -3 plus 5 plus -7. Every other one should be negative. And so we can do that by just saying, hey, sign is going to be the sign of I. Okay, so if I do this right now, nothing changes because, again, I didn't tell sign to do anything. I just said sign is equal to 1. We actually have to put in the code. So what we're going to do is each time we're going to print out the equation, generate the total, update the total, and now we have to add in another step, which is to take our sign and do -1. So sign is equal to sign, sagne, sign times -1. Okay. And so now what we see over here is that we do see it alternating, 1 plus 0. Let's see. Oh, but that doesn't seem to be right? It is 1 plus 4 plus 9. Sorry, it's still 1 plus, even though I'm saying I'm adding a -3rd, it's not actually doing it, right? Let's open up our code a bit more, right? I'm just simply printing out sign times I, but what's going on? When I'm playing with total, I'm just adding in I. I haven't fully added in the sign yet, right? I haven't added this in, so I need to make it plus sign times I. It might actually be easier instead if I do this. Just a bit of a stroke of brilliance over here, I think, in my part. Not really, but what we're going to do here is that we are going to say I is equal to sign times I. So that way I don't have to remember to change all the I's, right? I don't have to change all the I's to sign times I. I'm just doing it over here. Does that make sense to everybody? Okay, so what I can do here is now see, and now we've got some alternating values. 0 plus 1 is 1, 1 minus plus -3 is -2, -2 plus 5 is 3, 4, 1, 2, 3, 4, 5, 6, and it just alternates going up like that. That works. So we are adding our values in. Again, it would be cool if we could just do negative signs in here, minus signs instead, but honestly, this works for this. And we're going to have to say goodbye to it in a bit because honestly, printing we're going to get to points where we don't know what we're adding because most of us don't have like 1/7 or 1/9 memorized, right? Although 1/9 isn't that bad. So we need to get to here. 1 minus a third plus a fifth minus a seventh. Sorry, not minus 7. Wow, that was been in there for. You see, that's what happens when I write and talk at the same time. It's part of the reason why when you're watching a math professor put stuff on the board, they're not talking. They're typically silent. Okay. This might be a bit easier to see if I do this, by the way. 1/1, right? what we need to do is turn all these, and so if we look at that, you can go, wait a second, what I need to do is turn all these numbers into denominators, right? The numerator is never going to change. It's always going to be 1 over this number. In other words, it's turning into what we call the reciprocal, long story short, to make it 1 over this number is actually, it's one of those things that you see, if you are not seeing it now, it's one of those things, if you see it, it's hard to unsee. That's it. That's all we need. Which is I is equal to 1 times the sign over whatever the value is, right? So this is going to turn 1 into 1 over 1. It's going to turn 3 into 1 over 3. It's going to turn 5 into 1 over 5, and so on and so forth, right? Let's see. I is still here. Is it? Let's see. No, apparently not. What did I do wrong? I is equal to sine times I. 1 is equal to sine times I. Is it 1? What am I doing wrong here? This should set the value. And what am I getting over here? I am getting 1, negative 3, 5. Do I need 1.0 to begin with? I doubt it. That shouldn't matter. Oh, right. Silly me. Order of operations. So this is not, I can't write a fraction, right? I'm interpreting this as a fraction, right? 1 over divide, right? I'm trying to do this as 1 over, but this is 1 divided by sign, so it would be divided by 1 or negative 1. So this value is either going to be 1 or negative 1, and then I multiply it by I. So hence why it wasn't going out. So what I really mean is this. What I really mean is this. So we need our parentheses here to do that. And now we're starting to get some results here. 1 plus 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th, right? We see that now, right? So we could ostensibly make this a bit easier on our eyes to read by saying, by kind of undoing what we just did over here. This is going to look hella weird. I'm just going to do this for the heck of it because I've never done it like this before, but it's a weird way to do it. 1 over that, and then plus, you don't have to copy this down. 1 divided by. Is it even, no, that's going to just look terrible. Oh, no, looks okay. See, 1 minus a third plus a fifth minus a seventh. It's the ninth. We could make it do, but honestly, we've got our point across at this point. That overcomplicates it. Let's keep it simple. Keep it easy to read. Nope. I said keep it easy to read. And so we see this value, 1 minus a third plus a fifth, and so on and so forth. Let's go ahead and just simply print out the total instead. Because now it's just a mess of decimal numbers that we're adding together. So what we can see is that this value is starting to remain kind of at the same point, right? In fact, if we increase our limit to like 500, we'll see it remain, it's starting to really remain at like 7.8. Which, again, what is the point of this entire sequence we're doing? We're trying to say it's close to pi over 4, right? So if I multiply, if this is going to be, if we're trying to generate pi over 4, well, I don't know pi over 4 off the top of my head, but I do know pi pretty well. So what I can do is, this is pi over 4, I can multiply this by pi, okay? Sorry, this by 4 to get pi instead. And now, if we're multiplying these values by 4, you're seeing something over here. It's trying to really hover somewhere around pi, 3.1413. It's getting there. So, as I mentioned, also printing is an expensive operation. Take, for example, how long it took to do that operation versus if I don't print anything out except the final number, it just instantly prints. Printing is relatively expensive because your screen has to update and stuff like that. So this is, after running it 500 times, we get 3.13. That is not pi. I never said this approximation was good or fast, did I? But it is an approximation that works. And if I do it 5,000 times, 3.14, 1. So this is supposed to be, this is actually very interesting over here, right? What is pi? It's 3.141592653. Wait a second. 3.1415, that's not a 5, 92653. It's actually fairly accurate except for like that one variable, sorry, that one decimal point over there. And that's like a weird quirk of this progression. 3.1415926, right? Single variable off again. Or sorry, single digit off. If I go up to 500,000, 3.1415926, so okay, 2 wrong over there. But like it's funny how close we are getting. And that took a bit of a longer time to generate. Right now we are generating up to 1 over 500,000, 5 millionth, 1 over 1 5 millionth. So this algorithm is running 2,500,000 times, half the, right? Because we're going up to we're going up to a limit, but we're only doing every other number, right? Like if I was doing up to 500,000, that goes pretty fast. But if I add another digit, if I do 10 times as many, it actually takes a bit of time to generate. And if I go up to 50 billion, this is what we in the business call a linear time algorithm, or O of n. You'll learn more about this if you take higher level classes, but essentially most algorithms, they basically work one of two ways, which is they are either linear or quadratic. They will, if linear meaning that if you tell it to do it, if you multiply the number of times you're going to perform an operation by 10, it's going to take 10 times as long. The other way is quadratic, which says if you're going to do 10 times as many operations, it's going to take 100 times as long. Why would that happen? If an example is me grading, the example I like to use is it's linear time for me to go through your exams and grade it, right? And if I take one more test, that's going to just be one more unit of work, right? But if I am being very paranoid for some reason and checking everybody's answers against everybody else's, each student against every other student's, that's going to take a while. And adding an additional test, like a student turns to their test in late, that's not one more thing to do. That is n more things to do, where n is the total number of tests. I have to go now check the student against every other student. Obviously, that's overly paranoid, and I don't do that. But it's a good example. It's a good visual example of kind of those different rates of growth. Is that going to be on the exam? Hell no. This entire thing was to kind of to build up to this this monstrosity of a for loop over here. It's a monstrosity early on, but it is, and this is definitely way harder than what I would put on an exam. And so while we're here, I guess I might as well talk, since we are getting, so this is week 3. Like I said, week 6-ish will probably be the exam. I have to go and figure out about that. But let's go ahead and just kind of give you an idea of what the kind of things I do put on an exam. I do give out a practice exam every semester for the vast majority of the exams. And now that you have the kind of idea of what's going on in this class, right? I generally have like a basic true-false questions kind of things here about history. Computer science is the study of computers. Alan Turing is often considered the first programmer, who is Ada Lovelace, right? And then we've got these order of operations. You don't have to worry about this for, again, a couple weeks now. Order of operations, evaluate these expressions, true or false stuff, which we get into, about, and then this is still stuff you have to learn about slices, but a lot of the things you learn about learned about ranges today help with slices. For instance, this is basically going from what we call index 3, but up to, but not including index 8, right? It's just a different notation. Turtle drawing using a for loop. You'll notice that, and remember, we just started learning for loops, but we're going to get practice in what we call nested for loops. And that's part of the reason why I love turtles, because they help us learn how to nest these things. Right? Using the draw square function, write a program that will do this. And like I said, I like to make these things harder, and you'll be surprised as much as you learn. But there are these questions here about doing for loops, and you'll learn how to do them over time. Right now, again, this is like our second exposure to for loops, but for loops are really what you need to master it. And we do a lot of for loops to kind of do turtles. And we can do, since we have the time, I might as well show you like some fun stuff we can do with turtles, okay? With our for loops now. Because I really want to make sure we have time for this. This is really good stuff. So I'm going to call this spiral, because I'm going to show you about spirals today. Spiral. So remember our magic phrases right now for turtle are import turtle. Okay, and to create a turtle, I go Bob is equal to turtle.turtle. And I like Bob to actually look like a turtle, so I always do this. Bob.shape is equal to turtle, because, you know, I can do that. Another thing you can do is you can change his color. Bob.color is equal to red. You can change his color, and that's what we're going to play around with. Color is fun because it accepts an actual color. But you can also do this. And this goes back to actually our lecture number 2. Red. So 1, 0, 0. If I do 0, 1, 0, it gives me green. And then if I do 0, 0, 1, I get blue. Okay, so simply put, right? If you recall that every little square, every pixel on your computer is made up of 3 tiny little lights: red, green, blue. Right? There's not 4 lights or 5 lights. There's only 3. So there are 3 lights, and each basically represents a little light, and you can control how much you turn it on. So this means the red light is off, the blue light is off, the green light is off, the blue light is on. If I turn on the red light halfway, we get a purpley color. Okay. Now you might be thinking it's a bit weird because. But remember, this is basically we're adding light, we're not adding paint. So the color mixing is going to look a bit different than you'd expect, right? Because when we add colors together, when we're painting, we get all black. When we add light together, we're going to get something completely white, okay? It's just the nature of just doing different color models, as they're called. Okay, so why do I care about this? Well, we've used a for. We now. I'll leave this up for a second. We've used a for loop now, and we can use it in various ways to do stuff. The first thing we can do is, if you remember, we learned how to use a for loop to draw a square. For blank, in range, for. I figure and why am I doing this as opposed to letting you out early? We just did something that went from simple to very complex, so let's go back to doing something a bit more simple to end it with, right? To make sure that you feel like you're getting stuff out of this. More practice, more good. Okay, let's go ahead and say bob.forward 100, and then bob.right. So he goes forward and then he turns right. And he just does that. 1, 2, 3, 4. Okay? That draws a square for us. Right? And we showed that we could basically make this arbitrarily large, and it will just keep running. Right? And he just keeps doing that. But we've learned how to use variables inside of, as part of a for loop, so we can vary what Bob does. What do I mean by that? Well, right now I'm having him move forward 100. Why don't we try this? For I in range 40. Now, we could do something like, we could do something like this, but you're not really going to see anything interesting. But we start to see something, which is that, well, because I is changing, the amount Bob is moving, each side changes. The first side he moves 0 times, then he moves 1 pixel, then 2, then 3, then 4, then 5, then 6. It's a bit hard to see because it's just so tight, right? But he's obviously started to move a bit more than that, right? And he ended up by moving 39 pixels. Really not that great. So we could scale this a bit. I times 5, so 0, then 5, then 10, then 20. And now we start getting something that is recognizably a spiral, right? Okay? So we can use this variable over here to have a lot of fun with that, just to kind of move him over time. Let's go ahead and make it an even 50, because that's going to make some computations we're going to do in a bit easier. Or at least mentally easier. So here he starts out at moving nothing, then 5, then 10, and so on and so forth. If we wanted to make it a bit of a looser one, that error just happened because I closed it impolitely. I could start out at 100, right, and then add this value in, right? And then it still generates a spiral like that. Okay, but it goes quicker if I start from the tighter angle. Okay, now the other thing is that if I put a color statement inside the for loop, that will reapply the color statement whenever it hits it. So I could just simply say, you know, hey, Bob, set your color to red each time, and that's just kind of a waste of a line because it just tells him to be red all the time, every step of the way. But we've learned how to use a variable, and if we know how to use a variable, we know how to vary something, right? So we can vary this. We can say, hey, we've got this value. Let's go ahead and, it would be tricky to, so first off, does anybody want to tell me why doing this would be problematic? Division by 0. 1 divided by, right, I starts at 0, so if I do that, I divide by 0. There's a couple ways to get around that. The first way is to just tell it to start at 1. So we'll go ahead and do that. And if I do this, it gets dark pretty quickly. So that's obviously not what we want to do. What we want to do maybe instead is we'll go and say I minus, and let's go with, let's see, 0.1 times, let's go with 0.01 times I. So right, I is a value between 1 and 0, and what we're going to do is we are going to subtract 1/100th of it for every step we take. Now if we see that, we can see that he's going to slowly darken, and it's slow and subtle. It's very subtle over there, honestly. But now he's noticeably darker. So let's go ahead and see, let's go with I times 1 over because we're going up to 50, let's do 50. I times 1/50th, and that will go all the way down to fully dark. And then that's going to go all the way from red to fully black. But let's go ahead and actually give it some color here. What we're going to do over here is we're going to go from 0. We're going to say I divide by 50 over here. So we're going to go up on the blue and down on the red. So it's a bit hard. Again, it's a bit harder to see. If you're following along your computer, this is now easier to see. You see red versus, you see a red center and a blue outline now. Right? You can do that. So you can vary, just with this bit of knowledge, you can do some fun variants of things. Also, there's nothing stopping me from, also, it's very interesting if you don't do right angles, but you do something close. Right? If you do something close, that gets pretty interesting. We can also group it up a bit, and that's where our nested loops can really come in. I'm going to go back to doing this. Promise it's not going to get too scary. So here, we're going back to what we had. But you can nest for loops. You can put them inside each other. And I'm going to make this one fairly uncomplicated. For blank in range 4. Why am I doing this? So what I'm going to do here is I'm going to say for 50 times, draw a square. This is what this does. This is drawing a square. Right? All I did is I took the code to draw a square and put it in kind of one statement. So it's going to draw 50 squares, right? 50 times 4 forward motions now. And then I'm going to apply the color change. So and if you know, it's a bit different too now, because why? I'm telling it to move forward. Every part of the square is as big as the other part of the square. So I believe actually what I need to do here is I have to mess with this a bit. So move forward, I times 5, and then 4, then not another 4, but Bob dot forward 10, I believe. Oh, I misspelled forward. That's not going to do spirals, but hey. You get progressively bigger and bigger squares. And they overwrite each other, which is fun. And so drawing these weird geometric patterns, this is really what we can be very we can be very good about with these turtle things. So that's one thing we can do with it. I'm going to copy, going to comment it out for our last thing, right? Get rid of this again. We're going to just go back to being a bit easier to see, right? And let's go ahead and let's do 61 hexagon, but not quite. So again, by making simple adjustments to this program, we can have a lot of fun with it. All right. So speaking of fun, I hope you have fun this weekend.